Yeah, alrighty, and welcome to the final lecture, I guess, of this course. Um, I hope you guys have been happy with how it's gone. There will be a evaluation, course evaluation circulated to you at some point soon. I talked to Margaret about it, so I think she's going to coordinate that. So there'll be a chance for you guys to comment on what you've thought about the course, how you felt about how I've done teaching it, ideas for what can be done the next time I run this, etc., etc. So that's all very valuable feedback. So I hope that you fill that out when that gets circulated. But in the meantime, today is radio emission mechanisms and polarimetry. And so I know that a fair chunk of you know a lot about polarimetry already. And so some of this may be review, although I've tried to focus most of the conversation on polarimetry around observational aspects and on sort of like the data calibration aspects to sort of keep it in line with the earlier parts of the course. And so some of that may still be new and interesting to you. And so leading off with just a quick talk on radio emission mechanisms, and I want to focus this primarily on sort of the observational properties and characteristics, since I know there is a separate course on radiation processes, which many of you either have taken or may take. And so there's no point in me repeating the details that you may cover through that course. And so very quickly on sort of what the main radio emission mechanisms are that we encounter most often, what some of their observational properties are, and then maybe a few quick words on some sort of applications of radio astronomy that involve using or interacting with these different emission mechanisms. And so these are the main four, at least so far as I'm aware: thermal emission, spectral line emission, bremsstrahlung free emission, and synchrotron radiation. So I'm going to go through each of those over the course of the next little while. And, before I get into them, I just wanted to talk briefly about the concept of the spectral index, in case you have not seen it discussed, which is we typically like to talk about radio spectra in terms of power laws, which is sort of the standard form of a power law with some intensity at some reference frequency and a power law spectral index, generally called alpha. And so when we talk about the spectral index, that is basically defining this power, or equivalently the slope in a log intensity, log frequency plot. And a surprising amount or variety of radio emission does tend to follow power laws. And so this is a fairly useful tool, which comes up a lot. And in cases where it doesn't follow a power law, there is a tendency to just kind of force it into that kind of mathematical structure. Anyways, people start talking about spectral curvature, which is adding kind of additional terms to this. Or you can talk about a frequency-dependent spectral index, where the spectral index is effectively just the derivative or the instantaneous slope in a log I log frequency plot. I guess one sort of side aspect I want to mention actually is that some people define this with a minus sign in front of the alpha. So this basically just flips the sign of alpha in whatever discussion uses a different definition. So I generally use the positive definition written here. Some people will report the negative one. Just sort of be aware in case people ever start talking about spectral indices that have a different sign than you think they should have. It's probably just they're on the different convention. And one other complication is in the brightness temperature units, where we have this conversion from intensity as a function of frequency to brightness temperature as a function of frequency, defined thusly. when people are dealing with brightness temperature, which is quite often in single dish data. People like to use brightness temperature a lot, and they define power laws there as well. But because there's the extra factor of frequency squared in this conversion, you end up with a different slope in your brightness temperature versus frequency plot. So you basically end up with a different slope, a different spectral index, and it's just basically 2 lower than the spectral index in intensity. And so this can trip you up if you don't know about it. So I thought I would point it out. Because this got me during my own PhD. I was used to people talking about synchrotron radiation with spectral indices of like -0.5, -0.7. And then suddenly one of my co-authors was saying, yeah, the spectral index for synchrotron radiation is -2.5. And I had to sort of stop and think about this for a bit and then be aware of why his was 2 units lower than what I was used to thinking about. Any questions on that before I jump into black body radiation? Okay. So black body radiation is something I think we're probably all generally familiar with from undergrad physics mostly. Follows the Planck black body law, which is a rather messy function, although in the radio regime, we are effectively always in the Rayleigh jeans limit or approximation, where you can basically just write it as this frequency squared function. And so immediately from that, we get that the spectral index of black body radiation in the radio regime is 2 in the ideal case. And so that's a very characteristic signature of black body radiation, although things can get a bit messier, and I don't actually know that much about what this does. All I know is it is a thing, but you can get complications like modified black body laws, whatever those are, optically thin black bodies, et cetera, and this can do more complicated things to your spectra. I've seen this in the context of things like dust emission, things like dust grain size. Different size dust grains have different black body efficiencies, I guess, that kind of a thing. So it can get more complicated. It's worth noting this, spectral index is typically about +2, which means the intensity gets higher as you go to higher frequencies. And so thermal emission tends to dominate at higher frequencies, at sort of 100 gigahertz regime or sort of that kind of high frequency regime. We don't see much of it in sort of the gigahertz band and below. And thermal emission is intrinsically unpolarized, which is, I'm going to sort of discuss this and which mechanisms are polarized sort of as preparation for the final section, I guess. So this is sort of a couple of examples of typical black body spectra. And what I wanted to highlight with this is basically how high in frequency you can go and still be in this Rayleigh jeans power law limit. And so even at a temperature of down around 10 Kelvin, you're in this regime up to about 10 to 11 hertz, up to about 100 gigahertz, even with a 10 Kelvin black body. And so anything below 100 gigahertz, you're always in this Rayleigh jeans limit, even probably with CMB. And so it just sort of makes things so much simpler to not have to deal with the full Planck function. Yeah. Gas lines, spectral lines, come in a variety of types, but we're sort of should be generally familiar with sort of the basics of it. There's a lot of different variations. So the electronic state transitions that we're maybe used to in terms of like the hydrogen Lyman and Balmer series. But there's additional types. Hyperfine splitting shows up. Rotational vibrational transitions of molecules tends to show up, et cetera. And any kind of transition or different sort of quantum states that can occur in gas, you'll generally see lines for. One thing that's interesting to note is in the radio regime, many of the lines have very, very narrow natural line widths, to the point where it's effectively, you can't see the natural line width, and so all of the structure in the spectral lines is entirely due to Doppler broadening, and so you effectively get measurements of the velocity distribution of whatever the emitting or absorbing gas is. And so that can become a very rich source of information on the kinematics of your system. And additional information you can get is column densities, typically. Under some conditions, you can start to get temperature densities, ionization states. There's a lot of physics that goes into it that I know comparatively little of, so I won't spend time on it. And in addition, some lines undergo Zeeman splitting, Zeeman effect, due to magnetic fields, and this leads to polarization in spectral lines, although this tends to be circular polarization in many cases. And also, in a lot of environments, the Zeeman splitting is actually too weak to actually give you multiple resolved spectral lines. And so what you tend to get is spectral lines that are overlapping but ever so slightly shifted with different polarizations. So you end up with some sort of complicated polarization profile for the spectral lines. A few examples of sort of specific applications of different sort of gas lines. Most famous, of course, is the hydrogen 21 centimeter hyperfine transition. This is the spin-spin coupling in hydrogen between the electron and the proton, which when the spin flip occurs, produces a photon at 1420 megahertz. And so this is absolutely wonderful, because this then traces neutral hydrogen gas anywhere in the universe with remarkably little sensitivity to density, temperature, pressure, etc. So, and as I mentioned a couple slides ago, the natural line width is incredibly small. So all of the broadening is entirely sort of physical Doppler broadening. And so this, of course, then tends to get used a lot for mapping out gas distribution in galaxies, clusters, etc. It can also be seen in absorption. This is not purely an emission line. If you have a line of sight towards a very bright continuum source, you can sometimes see hydrogen absorption, particularly if you have sort of dense, cold clumps of neutral hydrogen that tends to produce stronger absorption features. Yeah, mildly interesting factoid on the hydrogen line is that the mean lifetime of the excited state for this transition is about 10 million years. And so it's a very slow transition in the sense that it takes a long time to deplete the population. And that lifetime is basically much longer than the expected collisional excitation time in the interstellar medium. So there's basically no risk of ever sort of depleting your population in the excited state, which is another reason that it's a very reliable tracer of hydrogen gas. Another very popular line is the carbon monoxide lines. So we can trace hydrogen in its neutral gas form. Ideally, we'd like to be able to trace it in the molecular form, since it is sort of the predominant ingredient in the universe. But sadly, symmetric molecules do not produce very much in the way of emission lines, because they lack, because they have this rotational symmetry, they have a lot fewer available transitions effectively. And thus H2 is a very difficult molecule to actually get good measurements of astrophysically. In contrast, though, carbon monoxide is asymmetric since the oxygen is heavier than the carbon. It has some very good lines, and it is an abundant molecule in most sort of molecular cloud regions. And so you get a sort of a rotational transition of CO at multiples of 115 gigahertz. The J1 to 0 transition is at 115 gigahertz. The J2 to 1 transition is at 230 gigahertz, and sort of so on, multiples of that. And so that, you can use that then by assuming some abundance relationship between the number of CO molecules and the number of H2 molecules. There's this ratio XCO, and then you can convert into estimates of the H2 mass, and since the H2 dominates, that gets you a sense of the molecular gas mass. And so there's been a whole slew of papers and research done into actually figuring out this ratio and how stable it is in different environments and over cosmic time, et cetera, et cetera. So that's definitely been a very active area of work and such. Another aspect of lines, this one is probably much less common, but I wanted to include it because I think it's cool. And that is radio recombination lines. And so, recombination being the conversion from plasma back to gas, the electron sort of being bound back onto the ion nucleus, forming neutral atoms again. And so when this occurs, the electron starts off bound into generally into some excited state, and then cascades down to the ground state. And we're kind of used to this in terms of optical spectra, because this is what gives us the Lyman series and the Balmer series and H alpha and all of that. All of those lines are basically the cascade down to the ground state. But there is a radio counterpart, and that's because sometimes these recombinations will leave the electron at a very, very high N state, states of several hundred N, and then the electrons take some pathway back down to the ground state. And there's some nifty aspects to this. Like when you get a hydrogen atom with a really, really high N, somewhere around 800, just the size of the electron orbitals is huge. Like this is apparently a 1 micron atom. It's absolutely enormous compared to the regular size that you would think of for a single atom. And it's such a large, fluffy atom. I think it's bizarre. And you end up with transitions then at sort of those very high energy levels that are really low energy transitions, down around 10 megahertz, 11 megahertz, up to a few hundred megahertz. And so you get these populations of atoms in these states, and you can see their lines in the radio. Under some conditions, you can even get absorption lines from these states. And so there's been some interesting work done recently just tracing cold phase ISM by looking at these really extreme atomic states produced through recombination. So I thought that was a cool little thing I'd like to highlight. Any questions on any of that? Okay, so continuing on with free emission, aka bremsstrahlung or braking radiation. And so this is emission produced in dense plasma environments where you have free electrons and ions. And yeah, this is basically just in terms of classical physics, you have charges interacting, accelerating each other, and this must produce radiation via Larmor's equation from classical electrodynamics. And so you get some sort of continuum broadband radiation out of this process. And the spectrum is actually a little bit messy. In the high frequency regime, you have some sort of classical thermal cutoff just because of limiting sort of the energy, kinetic energy available from the from the particles that are interacting. So you get some sort of typical kind of Planck cutoff at the high end. The optically thin regime has a very weak frequency dependence. It has a spectral index of -0.1 nominally across a fairly broad frequency range. And the exact frequency range depends on some conditions of the plasma. I'll confess I don't know all the details. And then at some low frequency regime, it becomes optically thick, and you get this spectral index of 2. There's this effectively black body-like low frequency regime. And so free emission tends to occur, tends to dominate mostly in these sort of intermediate frequencies. Sort of in between the higher frequencies, you start to get more thermal radiation dominating. At the lower frequencies, you tend to get more synchrotron radiation because synchrotron becomes brighter at low frequencies. And so the free emission tends to only be a significant component kind of in between, sort of in the lower gigahertz kind of regime. And the primary source of free emission tends to be H2 regions. So very, very dense ionized regions, Stromgren spheres, that kind of environment. Because this is effectively a collision type process, the intensity of the radiation goes as the density squared. So you need a fairly dense plasma environment to actually produce a significant amount of free radiation. So you'll see a lot of free from dense H2 regions, and then very, very little from sort of the diffuse ISM. One kind of fun fact about sort of diffuse emission, particularly from H2 regions, and I wanted to highlight this just to show an interesting aspect of interferometers, is that H2 regions can actually show up as having a negative brightness if you observe them with an interferometer. And so this is a little mind-bending, but I think it's an interesting example. So start off by considering a H2 region somewhere in the galaxy, and you want to observe it in the low frequency regime where it's optically thick. And so surrounded by, or specifically behind it, you also have diffuse synchrotron emission, which I haven't discussed yet, but you have some diffuse synchrotron emission which has a higher brightness temperature. So it's much brighter, effectively. But because the H2 region is optically thick, it is absorbing radiation from behind it. And then what you're seeing is only sort of the surface of last scattering closest to you. So the H2 region will effectively absorb the synchrotron radiation from behind it, and what you're seeing is only the brightness of the H2 region, which is dimmer than the sort of surrounding regions of sky where you only see synchrotron radiation. So take this and now observe this with an interferometer. An interferometer which is missing the zero spacings, the short spacing, so it's not sensitive to the very large structure on the sky. So you effectively lose the mean signal, which is dominated by this large extended synchrotron emission. It's too large for the interferometer to see, so it gets removed. And because the H2 region has a lower intensity or lower brightness temperature than the mean of the sky in the particular region of sky, it ends up having a negative value as measured by the interferometer. So, because the interferometer is missing the mean, you can think of the mean as being dominated by this large component. And when you subtract it off, the large component was slightly above the mean, and the little H2 region was considerably below the mean. So it becomes effectively a negative hole in your image. This is in a low frequency regime where you have this optically thick. And so you can actually look at an H2 region as a function of frequency, and at the very low frequencies where the brightness temperature is low and it's optically thick, you see a hole of negative intensity. And then as you go to higher and higher frequencies, the synchrotron tends to become weaker, and the free emission becomes brighter, and then it also stops being optically thick at some point. And so it has the net effect that at a higher frequency, then it is brighter than its surroundings, and you start to see positive emission at some point. So you can see it transition from negative to positive apparent intensity as measured by an interferometer. It's sort of a very bizarre effect. Okay, finally, synchrotron radiation, which is produced by charged particles moving through magnetic fields. So magnetic fields produce an acceleration on charged particles. And again, through classical electrodynamics, the Larmor equation, you expect some radiated power. And the full derivation is a bit of a mess and not really relevant today. But effectively, because the radiated power depends on the magnetic field, but also on the velocity of the particles, it turns out that thermal plasma does not have enough energy to really produce a significant amount of emission. But relativistic particles in the form of cosmic ray electrons do have enough energy and basically yield the vast majority of the radiated power. And so even though the density of cosmic rays, the number density is quite small, it has enough energy and radiates enough power to produce a significant amount of radio emission. And the spectrum of synchrotron radiation is vaguely similar to the free emission. You have some high frequency tail, at which point, at energies at which you stop having enough enough energy in your electron population. There's this intermediate region, optically thin regime, that follows a power law. And then in the low frequency regime, you get a sort of optically thick or self-absorbed regime. And for reasons that I've not entirely understood myself, the optically thick regime for synchrotron follows this power law of 5/2, 2.5, as opposed to frequency squared, like optically thick, free, or like thermal radiation. So you end up with a slightly steeper low frequency regime for synchrotron, and a fairly large optically thin power law regime where the spectral index is almost always negative, ranging somewhere between -3 and 0. And the spectral index of synchrotron radiation depends on the energy distribution of the underlying cosmic ray electron population. So what is the kinetic energy distribution of the cosmic ray electrons, which is also typically assumed to be some power law. And there's some equation relating the power law of the cosmic ray electrons to the power law of the synchrotron radiation. So measuring the synchrotron radiation spectrum tells you something about the underlying population of the cosmic ray electrons. And so this then becomes a very powerful tool for probing the cosmic ray physics of whatever system you're studying. Yeah, so a few comments on that. So the intensity depends on the density of the cosmic rays. It depends linearly on the density because this isn't a collision process. This is just single particles interacting with magnetic fields. And it depends on the magnetic field's strength. Spectral index, as I said, depends on the energy distribution of the electrons. In principle, there are also cosmic ray protons and nuclei. But because the radiated power depends on the charge to mass ratio, they basically contribute effectively nothing to the emission. The emission is almost entirely the very light electrons.
Hey, Cameron, can I ask a quick question?
Yep.
Okay, so normally when I hear about cosmic rays, it's usually like in the like intergalactic medium or ISM or something. Um, but I've never really, like, at least when you're talking about things like, like AGN jets and whatever, where technically you do have relativistic like particles, are those still technically cosmic rays, even though they're like bound to a structure? Like, I don't really know the full definition of like cosmic rays, I guess. I've never actually really done much with them.
That is a good question.
Sorry.
Yeah. I don't actually know. That
Okay.
to some degree it's a terminology thing.
Yeah, like I don't really know when it's a terminology or when it's still count. You know what I mean? Like,
yeah, I mean normally when I think about cosmic rays, or at least the cosmic rays in the environments that I deal with, which tends to be more regular ISM, the cosmic rays are more, or at least treated as sort of having more random motion. Okay. Like not having much in the way of bulk motion.
Yeah, that's what I thought, because I know people
they're mixed with non-relativistic material as well. So
okay.
That is a very different environment.
Yeah.
So I mean, yeah, when you have a relativistic streaming flow, what it's called, I don't know. I've not read enough papers on that to know if
no worries.
they call them cosmic rays. Yeah. No, that's an interesting
Thank
thought.
you.
There should be a lot of overlapping physics, if nothing else.
Probably, yeah.
Yeah. Where was I? Yeah. So what's quite often done is if you make some assumptions about the cosmic ray behavior, the density of cosmic rays mostly, it's possible to generally, if you can relate the cosmic ray density in some way to the magnetic field strength, then you can basically write an equation for relating the synchrotron intensity to the magnetic field strength. And so this is done to try to get magnetic field estimates of different kinds of systems like nearby and distant galaxies. And the assumptions are a little bit messy. Like the most common one these days tends to be equipartition of energy between cosmic rays and magnetic field, assuming that they have equal energy density. And I'm not entirely sure I understand the physical arguments for why that should be, although there have been a lot of papers trying to look at this in different ways to see if it's true. And the answer seems to be sometimes it's true on some scales in some systems. Another method that was used that's kind of gone more out of fashion these days was a minimum energy argument, which was, okay, if you make some assumption saying, okay, what is the minimum energy density of cosmic rays plus magnetic field, sort of the combined energy density, you want to minimize that to still get the same observed synchrotron intensity. And so this tended to be used a lot in sort of early AGN or giant radio galaxy studies to look at the energy budget of jets. To say, okay, this is the amount of energy in the synchrotron producing medium at a minimum, a lower bound in the energy, and therefore that amount of energy must have been supplied by the jet, kind of thing. So those kinds of arguments have been used in the past. One aspect to keep in mind is that synchrotron emission, because it's dealing with relativistic particles, it is intrinsically a beamed phenomenon, relativistic beaming. And that tends to be predominantly perpendicular to the magnetic field.
Sorry, I have a question about that.
Yeah.
So I had relatively general understanding that it was a beaming effect, but I didn't realize that was connected to the fact that it's relativistic. Is there like an obvious connection there as to why relativistic particles have a beaming effect?
Didn't know that either.
Yeah, kind of. And it's kind of like a length contraction sort of a thing. If you go through the special relativity of it, if you assume something like a particle in its own rest frame is emitting, well, it's not emitting isotropically, but I mean, you can look at a particle in its own rest frame. It's experiencing some force, some acceleration, so it's producing some radiation pattern. And then if you transform from the particle rest frame to the universe's rest frame or to the observer's rest frame, the whole length contraction things, you get angle, what's the word, aberration, is that the word? I think angle, there's a mapping of angles that's effectively what looks like, you know, sort of perpendicular in the particle frame of view is actually, you know, the faster the particle's going, the more and more it's actually moving with the particle. And I've
Yeah,
not,
you're actually reminding me that I think that I have read about this. I just completely forgot about it, and all I had remembered was that the width of the beam was like inversely proportional to
gamma, yeah.
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 But yeah, I'm actually remembering that now. So thank you for reminding me.
Yep. Yeah. It's been a long time since I've done special relativity. It is in the back of my head somewhere. Yeah. And so that's effectively it. And so the idea is you have some magnetic field line, relativistic electrons gyrating around. So they're always, you know, their motion is predominantly perpendicular to the magnetic field line, or at least their acceleration is perpendicular to the magnetic field. And so there's this kind of headlight effect, I guess, where, you know, as the particle is coming around, at some point in that gyration, it is, you know, looking towards you and therefore beaming in your direction. And so when the magnetic field is sort of perpendicular to the observer, there is a part of every gyration where every electron is beaming at you. Whereas if the magnetic field is sort of along the line of sight, the electrons are never pointed at you effectively. And so that's why ultimately synchrotron intensity relies mostly on the perpendicular component of the magnetic field, perpendicular to the observer's line of sight. The second aspect of that, although it's not relativistic, is that there is a net polarization to synchrotron radiation, and it is also perpendicular. Well, it's perpendicular to the component of the magnetic field in the plane of sky. So if you have a magnetic field line, the polarization is always orthogonal to that. And the strength of that polarization depends actually on the spectral index of the emission, because it actually goes back to the underlying electron energy distribution. So I can't remember how it goes, whether the more energetic electrons have better polarization or more polarization or less. I don't actually remember, to be honest. But you have that dependence. There are some equations for it that you can look up if needed. And it does also depend on the amount of order in the magnetic field, because you can imagine a completely uniform magnetic field, all the electrons gyrating the same way, producing the same polarization, it all adds up. If you have a magnetic field that's more tangled, you get different polarizations at different locations, and sort of the polarization vectors cancel out. So that tends to pop up.
Please, could you explain a little bit what polarization means in this context?
So that's a very large question.
Can't you just think of it like the electric field vector that's coming from?
Yeah, I mean, I'm trying to be more specific if I can. I mean, so yeah, the radio emission. I mean, yeah, polarization is the next section of the lecture, actually. Yes, let me put it this way: let me, since the next slide is the beginning of polarimetry, why don't I go through the polarimetry part, and then afterwards, if you have a question to help me sort of narrow in on what you'd like to know, then we can discuss it then. Are there any other questions about radiation, synchrotron radiation, or the other mechanisms?
What I want to ask is how, like, yeah, Jessica talked about the gamma being responsible for the beaming of radio, exactly. So, but I think this beaming is only for synchrotron. Do you think we get beaming from the free or even the inverse Compton part of radio emission?
No, I don't think so. No, I mean, free for sure doesn't have significant beaming because that's basically thermal particles.
Right. So my question there is, what about gamma makes synchrotron the only one beamed? Like, can we tell the gamma for inverse Compton or for, I think, yeah, there may not be gamma for the free because it's not necessarily relativistic, but for inverse Compton and for the synchrotron.
That's a good question. I don't know enough about inverse Compton, I think, to actually say.
All right.
To be honest, yeah, I've never actually looked at inverse Compton in any amount of detail.
Okay.
So I don't have the physics of it in my head, sadly.
All right, thanks.
Yeah, sorry. Yeah. Yeah, anything else? Okay. So polarimetry is a topic near and dear to my heart, and one that I've kind of put off to the end because I was afraid I would accidentally fill the entire course with it. Although it's kind of one of those things that it kind of does touch on a lot of the topics that we already discussed in previous lectures. And I've kind of been skipping over those parts. And so now a lot of what I'm going to talk about next is going to go back and fill in some bits of things relating to antennas and relating to interferometry and such. And so the reason that polarimetry matters, even if you're not interested in the polarization of whatever physical source you're studying, is that the antennas themselves are intrinsically sort of polarization aware. You know, any given antenna can only be sensitive to one polarization of light. So, you know, typically if we're talking about cross dipole antennas, you have one antenna sensitive to the X component and one sensitive to the Y component of the polarization. And so you need both to actually fully measure the signal. And the same if you're talking about left and right circularly polarized antennas as well. So ultimately your antennas are polarized, and even if you don't care about the polarization, you still need to deal with them in order to get your signal out for whatever measurements you want to do. But I mean, the polarization is also useful for giving sort of an additional source of information on different kinds of physics of whatever it is that you're studying. And in general, polarized emission generally means that there's some kind of preferred axis, some kind of symmetry breaking involved. And the most often mechanism for this is a magnetic field, which is why polarization or various aspects of polarization show up in nearly every form of magnetic field study in the radio regime and outside the radio regime, actually. So yes, everything we want to do in terms of studying magnetism tends to involve polarization. Not all polarized emission is intrinsically magnetic. I say that, is that true though? I'm having a hard time thinking of any polarization process, at least in radio astronomy, that's not tied back to the magnetic field in some way. But that could be my own biases speaking. But
from what you said, that one antenna can only see one polarization. So does it mean that you can't use single dish for polarimetry?
So you can actually. So a single dish, even if we talk about it as being a single dish or a single antenna, will almost always have two physical antennas mounted in it. It'll actually have two separate dipoles,
okay,
or two circular antennas
sitting
inside of it. And so nearly every modern instrument will have both polarizations measured. Like some of the early generation radio telescopes would only do one because they either didn't have the electronics to do two, or they didn't have the budget or something. And so there are some sets of old telescopes or smaller telescopes that only have one polarization, and they tend to be a little bit funny trying to analyze. But the vast majority of modern radio telescopes have both. Yeah. Any other questions?
I thought you were going to explain more what polarization means here.
Yeah, kind of. So let's start with this, I guess, in terms of the basic physical picture. So this is, we're sort of used to seeing these kinds of pictures of an electromagnetic wave, where there is the electric and the magnetic component of the wave, and where we always consider the electric field component, and there are two sort of sets of basis states that we can use to talk about polarization. So the classic one is linear polarization, where you have a coordinate system where you can say, okay, you can define any electromagnetic wave as a combination of one that is oscillating along your vertical axis and one that is oscillating across your horizontal axis. And any combination of those bases, those two states, can be used to describe any electromagnetic wave. So any wave is a superposition of those two components. However, it is equally valid to describe any electromagnetic wave as a superposition of two counter-rotating circular polarized states, where the electric field is rotating in a circular pattern, and this can be either clockwise or counterclockwise, or we tend to call them left and right circular polarized states. And so those, you can also build any electromagnetic wave out of a combination of left and right circular waves. And so we generally switch between those two basis, I want to say, is basis state the right word? Well, the two alternative bases, I guess, depending on which is sort of more convenient for the problem at hand. So they're both equivalent, and switching between how you think of an electromagnetic wave as being built up of these or built up of these is just a simple mathematical transformation. So we're free to use whichever one we like and switch as we like whenever we're sort of dealing with the mathematics of this. And either one can describe any polarized wave. And so in sort of the most general case, we end up with an electric field that traces out an ellipse. As over the course of one wavelength or one period, the electric field will trace out some shape that in general is defined as an ellipse. You can have special cases of this, for example, where the width of the ellipse is 0. You just have something that's oscillating in a plane as a linearly polarized wave. You can have a wave that's where the electric field is going purely circular, a purely circularly polarized wave, as sort of special cases of the ellipse, which is the general case. And I'm not going to derive that. That's in optics and E&M textbooks. So if you're sort of curious how you get to that, you're welcome to go into those. And so in general, every period, the electric field will trace out an ellipse. And there are different ways that we can define an ellipse mathematically. There are sort of different parameter sets we can use to describe an ellipse. One of the easiest ones is you can talk about a semi-major axis, a semi-minor axis, and an orientation angle, for example, as shown on the left here. And so with those three parameters, you can uniquely define any ellipse for which could describe any polarization state. But there's alternative combinations of parameters that you can use. For example, you could describe it as, again, like a semi-major axis, which I've written as root P. So bear in mind, this is all in electric field units, because we're talking about the actual EM waves. But we can define parameters in intensity units, which is electric field squared, like in power units. So we could define a parameter P in power units, and then the square root of P is the electric field amplitude, the semi-major axis. And then instead of a semi-minor axis, you can define a ellipticity angle, which is effectively the opening angle of the ellipse, where 0 is collapsing it to a line, and a 45-degree angle would be a circle, effectively, because you'd have equal semi-major, semi-minor axes. So it's a bit of a weird substitute for a semi-minor axis, but it's easy enough to define mathematically. And then again, a tilt angle, a polarization orientation angle. And this combination turns out to be kind of interesting in terms of its mathematical properties. Oh, I should back up a step according to my notes. So one little kind of mathematical complication is the electric field can, as it goes through one full cycle, one through period, it can either move clockwise or counterclockwise through the ellipse. And so that also contains physical information, and so that needs to be captured in the parameters. And mathematically, you can capture that by making, for example, the semi-minor axis can be a signed quantity. It can be positive for clockwise and negative for counterclockwise, for example. And you can do the same thing with your ellipticity angles. You can make it positive for clockwise, negative for counterclockwise, or vice versa. And so all that does is that encodes the direction in which the electric field is sort of traversing around this ellipse. So this is all very abstract, but it is going somewhere. And so particularly this set of three parameters here is a little bit bizarre. But if we take a look at it, so we have an amplitude parameter. We have this inclination angle or polarization angle parameter, which varies between 0 and 180 degrees. So if you look at this ellipse and you rotate it by 180 degrees, you've got the same ellipse again. And so polarization angle here is only actually defined over a 180 degree range, because if you add 180 degrees, you're back at the same ellipse again. So polarization angle is only defined between 0 and 180. And if we look at this ellipticity angle, it's also limited. It's only defined between, well, as an unsigned quantity, it's defined between 0 and 45. Because if you think about, if this goes larger than 45, then this axis has become larger. And then now that's the semi-major axis. So as long as you impose this criterion that the semi-minor axis has to be smaller than the semi-major axis, then the maximum that this angle can be is 45 degrees. And if we make it a signed quantity, it can go from minus 45 to plus 45. So now we have an amplitude parameter, an angle that goes 0 to 180, and an angle that goes minus 45 to plus 45. And so this, if we take those limits and we double those angles, this is basically a spherical coordinate system. And so we can define now this spherical coordinate system, which is the parameter space of any possible polarized wave. So any polarized wave, we can define its polarization in terms of these three parameters, and it sits in this parameter space, where we have the amplitude of the wave, we have this polar angle, or technically an equatorial angle, which is the ellipticity, and this azimuthal angle, which is the polarization angle. And so, yeah, so the power of this is we now have a parameter space that we can kind of think about all the possible polarized waves. And so all of the linearly polarized waves, all of the waves where the ellipticity is 0, sit on the equator of the sphere. So the equator is the parameter space of linearly polarized light. The poles then are the states that have maximum ellipticity. They're the circular polarization states, the left-hand circular and the right-hand circular polarization states. And it kind of makes sense in the sense that if you think about it, as you go to the pole, your polarization angle isn't defined. And for a circle, polarization angle is not defined for a circular polarized wave. There's no preferential axis to it. So this is all self-consistent mathematically. And so purely circular states are the north and south pole in this parameter space. The equator is the purely linear states. And everything in between is the sort of arbitrary elliptical polarized states of light. And so we have this sort of nice coordinate system for dealing with our parameter space effectively. And so yes, this is the Poincare sphere. And because we have a spherical coordinate system, you can just define a Cartesian coordinate system in that parameter space as well. And so these are the Stokes parameters. And they are a much more convenient representation of polarized states in some ways, because, I mean, just generally anything that's a Cartesian parameter space is easier to deal with than a spherical parameter space, in my experience at least. And so we define these 3 Stokes parameters, Q, U, and V, and they can be interpreted then based on the spherical coordinate system. So Q and U span the equator. So this is the space of linearly polarized waves. Q is where the polarization angle is 0. So positive Q corresponds to a polarization angle of 0, which is, in sort of going back to the ellipse, this would be a horizontally polarized wave. Is Stokes Q, or positive Stokes Q. Now, and this is a bit that will trick people up a little bit. If we consider negative Q now, negative Q is 180 degrees separated on the sphere, but because of these factors of 2 in the polarization angle here, this means that negative Q corresponds to a polarization angle that is 90 degrees separated from positive Q. So it's 90 degrees from the horizontal to the vertical. Negative Q is vertical polarization, where positive Q is the horizontal, because those two are effectively opposites in terms of polarization states. And so that defines Stokes Q. Stokes U then, we can see is 90 degrees on the sphere because of the factor of 2. That's a 45-degree polarization angle. So Stokes U represents the diagonal polarization. Negative Stokes U would be negative 45 or plus 135. It's the opposite diagonal, effectively. So Stokes Q represents the horizontal and vertical. Stokes U is the diagonal. And then Stokes V, as the poles, represents the circular polarization component. And so which of these represents right circular and left circular is a slightly complicated thing because there are different definitions. And so physicists have one definition for handedness in the Stokes parameters, and engineers have the opposite convention. And radio astronomy actually originated out of electrical engineering. And so radio astronomy has basically followed the Electrical Engineers Convention, the IEEE standard for defining left and right circular polarized waves, which occasionally messes things up if you're trying to read like a physics textbook and get definitions. So any definitions that you get out of a physics textbook, be aware that radio astronomy is the opposite in terms of left and right circular polarization. And so this is speculation, but I think the reason for this is that physicists, we tend to be thinking about light as it propagates. And so we're sort of looking down the path of propagation of an EM wave and saying, what does it look like? How is it acting? On the engineering side, you're maybe potentially more interested in receiving a wave. And so you're looking at it coming in and saying, what is it doing? And so there's this sort of difference in sort of watching it go and watching it come in. And I think that changes the handedness. That's my theory, at least. Okay. So the Stokes parameters now give us this Cartesian parameter space for polarized states. And it's sort of a nice, convenient way of describing polarized waves, because we can do things like, say, we can discuss what is the superposition of two waves. If you have two polarized waves and you add them together, what is the polarization of the combination? Because we can think of every polarized wave as a vector in this parameter space. Adding vectors in Cartesian is easy. Adding vectors in spherical polar is a nightmare. So this is the motivation for this, is everything is easy in terms of mathematical operations when you have a nice Cartesian parameter space. So any questions on that? It's very abstract, but I hope it made some sense.
Yeah, that was really nice. I have a question, but I don't know if it's going to be something that you'll end up talking about in terms of application. But I've noticed that whenever I'm reading about polarization in radio astronomy, everything's always really polarized. And I still don't fully understand why in radio astronomy there's not a lot of sources of like circular or elliptical polarization. I wondered if maybe you could...
Yeah, so that wasn't something I actually had, so it's good that you brought it up. And I think it's mostly just because there aren't a lot of emission mechanisms for circular emission. So if I go back here, come on. Actually, can I go? Yeah, it's just sort of looking through the list here. So black body emission is not polarized at all normally. Gas lines and masers are only polarized through the Zeeman effect, so far as I'm aware. And Zeeman effect, in theory, produces both linear and circular polarization. But for certain reasons, the circular emission is usually dominant. Without spending a lot of time on that. So yeah, Zeeman effect measurements tend to be dominated by measurements of usually very weak circular polarization. Bremsstrahlung is not polarized. Synchrotron radiation is predominantly linear. And so yeah, for most of our work, you know, since we're dealing with synchrotron radiation, we only really care about the linear part. There are some conditions in which you get a little bit of circular polarization from synchrotron, but it tends not to dominate.
I think Ryan has a whole book on like circular polarization and astronomy or something. Don't you, Ryan? Sorry to call you up, but I think you do. I think I remember you telling me about that.
Way to call me out on that.
Sorry.
You actually?
I do, yeah. Where is it?
Yeah, I was going to say, I'll defer to the expert then.
No, God, no.
I just remember you telling me you had a book on this, and I was like, what the hell even produces this type of radiation?
Is it a large book?
No, it's not. It's just very specific. All right. That's it right there.
Oh, cute.
By the way.
Oh, so it's also specific to jets.
Oh.
Also,
conference?
It's one of the, yeah. So it's kind of it's not like conference proceedings, but it's basically yeah, it's kind of along those lines. And this is a photo from the conference, and Brian's actually in the photo.
Oh my God. Of
Um,
course he is.
I think it was like 2004 or something like that, along those
Oh my
lines.
God. That's baby Brian.
Yeah. I mean, but from my understanding, especially like it's kind of relevant to what I'm doing with fast radiate bursts, is that I don't know much about like intrinsic emission mechanisms to create circular polarization, but there are definitely ways to convert from linear to circular.
That's actually what I was going to ask. Was that,
yeah,
sorry.
what I think.
Go ahead, Ryan.
Yeah, just one way to go about doing that is to rather than traverse through like magnetized thermal plasma, you just replace it with a relativistic plasma, and it changes the it changes the way that the polarized how do I say that?
Propagation, I guess.
Traveling through thermal plasma basically all it does is it rotates along the linear plane on the Poincare sphere.
Yeah.
Whereas if you travel through a relativistic plasma, it actually it rotates it in three-dimensional space in a frequency dependent way. So you'll get some frequencies that have more circular polarization than other frequencies.
Yeah.
So
okay.
yeah, that's the limit of my knowledge of that.
Sorry. So are you
pretty cool.
are you saying that for like the typical environment that causes Faraday rotation, which is like by definition from thermal electrons, not from relativistic electrons, that Faraday rotation through thermal electrons can transform linear polarization to circular polarization?
Not under normal circumstances. I mean, there is actually a mechanism to convert linear to circular. It's called Faraday conversion.
Right.
I don't know much about under what conditions it occurs. I think it has something to do with you have to have a magnetic field that is exactly perpendicular to the line of sight. So no parallel component at all is at least one of the conditions, but there may be more on it. But I know it exists. It's outside the scope of what I wanted to discuss today. Let's put it that way.
Okay, so I didn't mean to like totally derail this.
No, this is fine. But yeah, so yeah, it's worth commenting on that. Yeah, there is more to it. I also I completely forgot to talk about cyclotron emission when I put the slides together. So cyclotron is a low frequency low energy variation on synchrotron, and it tends to have more circular polarization, and I don't know that much about the specifics. So let's leave it with the comment that there is a lot more detail here under the hood to be looked at. If for people who are curious about more emission mechanisms and more about where the polarization originates in these mechanisms.
Okay, sorry that my question was somehow basic. I understand, like you rightly mentioned that physicists are looking at polarization as when light is propagating, and I think that's also my mentality about polarization. So when you're talking about it in context of astronomy, radio astronomy specifically, I still can't imagine it. So what do you mean when you say that an object is polarized when you're looking at it, or rather the emission from an object is polarized when you're looking at it? Yeah. How do you know that is linearly polarized and that is maybe spherically polarized?
Yeah, so I mean, when we say anything is polarized, ultimately all we're saying is that the radiation, the electromagnetic radiation that it is producing has a preferred polarization state. So for example, when I say something is unpolarized, like black body radiation, that means every photon has effectively a different or a random polarization. So every electromagnetic wave from a thermal source has different polarization properties. It's you know, it can be oriented in different ways. It can have different ellipticity, you know, and it's actually, to go back to the Poincare sphere. So what we can actually say is that for an unpolarized radiation source, every single photon or every single wave exists somewhere on the sphere, but they're all randomized effectively.
Is it like direction? Because you are kind of explaining polarization, or still using polarization.
Well, it's fundamentally, it is the orientation of the electric field component of radiation. So this is all in the plane perpendicular to where it's propagating. So you have a light wave that's propagating, and we have this plane that's perpendicular to it, and we can talk about the orientation of the electric field in that plane.
As it propagates.
As it propagates, yeah.
Okay, so it can change directions as it's propagating. That's what it means.
Yeah.
Okay, so
yeah,
how do you see this when you're looking at a telescope data?
Yeah, and so the orientation, the polarization of the wave affects how the wave interacts with an antenna, ultimately. Great. And so you can think about an antenna, particularly like just a straight antenna, as the electrons are being moved up and down the antenna. And so if you have a wave coming in and the electric field is oscillating up and down, you know, the electrons in the antenna are trying to move with the electric field. The electric field is accelerating the electrons. If you have a electromagnetic wave oriented perpendicular, so it's electromagnetic wave coming in, but it's oscillating along the other axis, the electric field, you know, is still trying to accelerate the electrons, but the electrons have nowhere to go along that axis. They can only travel along the wire of the antenna. Does that make sense?
Yes, yes.
And so the antenna then is only sensitive to electromagnetic waves that are oriented along that axis, the axis of the antenna.
Right.
With, you know, and so, you know, this is why you need two antennas. You have one antenna oriented this way to pick up electric field components from waves polarized this way. You have a second antenna polarized the other way to pick up waves that are oscillating in the other axis. And so between the two of them, you're sensitive to all orientations.
Oh, great. So this is for linearly polarized ones, right?
Mm-hmm. Yes, although, and this comes back to what I said in the beginning, that you can describe waves as, so any wave you can describe as a combination of a vertical wave and a horizontal wave at the same time. You can effectively break it up into two waves, sort of like this. That's what this diagram is supposed to show. Is any polarized wave you can break up into a horizontal and a vertical. And then you can say, okay, the horizontal component will react with a horizontal antenna and the vertical component will react with the vertical antenna. And then you can then talk about how that goes through the rest of your system and such.
Okay, that makes sense. Thank you so much. So, but how do you expect to see spherically polarized light if there are no antennas that will be able to detect such? Or do you think these antennas could still detect these spherical polarized ones?
Circular polarized, yeah, yep. Yeah, because the circular polarization, and yeah, I don't have good diagrams for this, sadly, but so yeah, if you have a vertical antenna and you have a circular patterned, circularly polarized wave, at some points, you know, the electric field is along or anti-parallel to your antenna. So at those points, the electrons will get accelerated, and then at some points there's no acceleration. And so to the antenna, a circularly polarized wave looks like a vertically polarized linear wave because it's not seeing the other component of it. And so it's seeing it as this, and it doesn't see the parts in between where it's going, you know, perpendicular to the antenna.
Okay.
So you can still build a circular wave out of horizontal and vertical components. There's a third parameter, which is the relative phase of these two. Sure. That allows you to do that.
All right, thank you.
Yeah, and I definitely recommend maybe taking a bit of time to look at maybe like an optics textbook, because they do a much better job of actually describing all of this and laying out some of the mathematics and some of the diagrams much better than I can do. I'm rushing through most of this, to be honest, just because I wanted to cover a lot of this very quickly. Right, any other questions on the topic of just polarization, ellipses, and Poincaré sphere aspects? Okay. Right, so so basically what this gets us is every single wave is a vector in this parameter space, and we can then talk about superpositions of many waves as vector sums, and so being able to combine them together, and then looking at sort of the net polarization. And so a unpolarized source is one where the vectors average to 0 if you superimpose, or if you sum together over time, for example. So we can actually bring this back to the quasi-monochromatic limit from the first lecture, where a wave is only defined within some time frame, like some coherence time based on its bandwidth. You can do the same thing here with the polarization state. The polarization state of a wave may only be well-defined within some coherence time, and then it can shift. And in an unpolarized wave, those shifts will be completely random. You will have random vectors. And when you try to integrate over time, you end up with 0. With a polarized wave, all of the vectors should be aligned with each other, and they should sum up into a net signal. But you can also have a partial version of this where there is some randomness, but some preferential direction as well. So you can get partial addition. And so what this means then is that the combination of, you know, the sort of the summation of polarized waves has sort of, you need an additional parameter to identify it, because we want to deal with time averages, but the time averages can, the time averages can average out to 0, even though there is always signal present. And so in order to capture that, we introduce a fourth Stokes parameter, which is Stokes I, which is the intensity, as we've already been discussing throughout the course. And so you can define this as, for every instant you have an intensity based on the length of your polarization vector, and you can just integrate that as a scalar quantity. So you always have some intensity, and you can just add that up as a positive definite scalar to describe how much power you have, how much intensity you have, as we defined back in the first lecture. And so with the 4 parameters then, I, Q, U, V, you can define the intensity, the time averaged intensity of the signal, and the other 3 parameters give you the full averaged polarization state of the signal. And so this then tells you what is the average polarized emission of this source within the time frame you've observed it. And so all of these definitions for the Stokes parameters then, we can define them. We've sort of started off by talking about them in terms of sort of single polarized waves, but you can basically propagate these definitions through all of the mathematics we've done in the first 3 lectures on correlations, on interferometers, visibilities, the single dish correlations and autocorrelations, all of this can get propagated through, including the fact that every antenna is only sensitive to one polarization state. And so that yields us to these sets of equations, which sort of govern the relationships between Stokes variables and correlation products. So previously in the interferometer lectures, I kind of avoided talking about different correlation products because I was pushing it off until now. So let's think back to lecture 2 where I was introducing visibilities and we were talking about correlating 2 voltage signals from 2 antennas. So we can still do that now. Excuse me. So we can still do that, but now let's bear in mind that for every dish, every antenna, we actually have 2 physical antennas, like an X and a Y dipole, or a left hand and a right circular antenna. And so we can then talk about, okay, I can correlate the X antenna from antenna 1 and the X from antenna 2 and get a correlation out of that, and that'll be an XX correlation. Or we can take the Ys from each dish and correlate those. Or we could take the X from antenna 1 and the Y from antenna 2 and correlate those against each other to get an XY correlation or a YX correlation. So we have, for every baseline, you know, you have two stations, 2 dishes, 4 physical antennas, and 4 correlation products from sort of correlating the different antennas at every dish. And together, those contain the full polarization information. And it sort of gives you the full information on the Stokes parameters of the signal you're observing. And so you can imagine, for example, the XX correlation. You have the X signal from the 2 antennas should be the same. And so when you correlate them, they'll always correlate well. And so that's why, regardless of the polarization, they'll always correlate. Even if it's random from moment to moment, at any given moment, they correlate with each other. And so that's why Stokes I goes into the XX correlation and so on. And so, yeah, I won't go through all of these equations. So the first set, so on the left, this is sort of for the linear dipoles. The right set is for the circular. And then top and bottom is just sort of correlation to Stokes and Stokes to correlation. I'm not going to go through all of these. They're a bit weird. It takes a little bit of time to actually think about where these come from and how it makes sense in terms of the signal processing and sort of what each of these correlations means and how it relates to the shape, like of the polarization ellipse. It takes some time. At the beginning of my PhD early on, I looked up the paper where all of this is defined, and I wrote these equations on a sheet of loose leaf, and I put it in my desk. And I went back to this a couple of times over the course of my PhD just to stop and think about this. And I found it helped me a lot. If this is the kind of thing you want to really sit and think about, because this really does define how the data, because what the data is really measuring is this X and Y antennas and the correlations and all of that. That is the actual data that you have. The Stokes parameters is the sky information. It's the polarization of the signal in the sky. And so relating the two can get a bit messy. And I mean, this is the whole sort of data problem, trying to get past the data to the actual information on the sky. And just because of the limited time I have, this is about as much as I can get into it, but it is worth spending some time on, I think. Yeah, I guess, so all of this sort of additional complexity sits underneath or as an additional layer to all the interferometry stuff that we talked about in the previous lectures. So in the previous lectures, I was, wherever I talked about like intensity and the Fourier transform of that, all of that, in principle, what we do practically is we talk, we measure these y correlations, we do the calibration on those. But because these are all just linear combinations, these simple linear equations, you can define a Stokes-I visibility by combining your XX visibility and your YY visibility. And this is what is actually done generally in software like CASA, is the data is measured in XX and YY, and you do calibration operations on those. But when you want to do things like imaging, CASA will turn those measurements into Stokes-I visibilities and do the imaging process like how I discussed in the last lecture in terms of, the whole sort of inverse Fourier transform and all that. So all of this mathematics is sort of sitting underneath in CASA, and all the heavy lifting is basically done for you. But some of this is good for helping to think about how issues in the data might manifest, in the Stokes parameters in the astrophysical signal and the images that you get out. And for example, if we just focus in on these, so when we do the calibration process, typically what's involved is we have a model for the source, which is typically a Stokes-I model saying, this is where the source is in the sky, this is how bright it is, right? Calibrate such that the visibilities reflect the model, right? You try and get the data to match the model. That's the calibration process. And so what can happen in some cases is the calibration process goes through this, it tries to optimize, but it's trying to optimize the data to match the Stokes-I model. So what it might not capture is if something goes wrong in calibrating X, for example, the Y calibration could counterbalance that such that the sum of X and Y looks good. It matches the Stokes-I model. But there could still be, because there's a mistake in both of them, when you then go to Stokes-Q, that problem compounds. It doesn't cancel out anymore. And so because of this, you can sometimes get calibration problems manifesting as Stokes-I looking good, and then your Stokes-Q looks like garbage. And in a circular feed, this goes to Stokes-V because it's the same sort of calibration challenge. And so there's this aspect that you maybe want to check your Stokes-Q and your Stokes-V. Even if you don't care about the polarization, you can look at them to see if there's any signs of bad calibration problems that can sometimes be masked because the data is not I and Q, it's not Stokes. And yet what the model is, what the calibration process is trying to optimize for is in Stokes spaces. So you can kind of get these problems, and sometimes it's worth knowing to look for them. Okay, so having gone through sort of all the sort of theoretical, mathematical basis of all of this, I wanted to talk a little bit about polarization calibration with interferometry data. And so this can involve a number of steps. I was able to think about 4 of them. There may be others that I'm not aware of depending on different telescopes working differently. And it's also the case that not all of these are always needed. And if you're actually not interested in the polarization data, if you just want Stokes-I, you don't have to do any of this. So calibration is designed so that you get your Stokes-I, your total intensity calibration out, and because that's the necessity. And then the stuff for sort of getting the other Stokes parameters properly calibrated tends to be extra steps beyond that. And how many of those steps you need to take depends a little bit on the instrument and what quality of data you're trying to get out. And so not all of these steps may be applicable to all data. Excuse me, I'm getting a little bit scratchy throat. Okay, so starting with sort of XY or left-right phase difference. And so I mentioned this briefly last lecture, I believe, where when you go through the calibration process, you calibrate all of the X antennas together and all of the Y antennas together. As part of the calibration, you do phase calibration and the gain calibration. So that's all done. But you actually have no linkage between the X and the Y phases because they're all calibrated relative to each other. And if you look at Stokes I, when you calibrate for Stokes I, you can calibrate the X's and you can calibrate the Y's, but there's no cross linkages because there's no cross correlations used in Stokes I. And so you end up with sort of two independent sets of phase calibrations. And they can be sort of not synchronized to each other, and that affects the other Stokes parameters. So this would affect Stokes U and V in the case of linear feeds, and on the circular feeds, it affects Stokes Q and U because they have to do with these crosshand correlations.
All right, I just have a super minor thing. So while you have the slide up, the very last equation that you have, is that supposed to be left, right? The very last one? Okay.
Yes, good catch. I will fix that actually.
Right, left, and then left, right. I just wanted to.
Yep.
Cool. Because I took a screenshot of this and I was writing it all down because you said that you had done that. So I thought that I would.
Yeah, well, I'm also going to post the slides, but although now that you pointed out is which one of these is RL and which one of these is LR?
Yeah. So it kind of looks like it's.
Well, hold on. We can figure this out because RL should just depend on Stokes Q. So yeah, this is right, I think. Or no, hold on. I will figure this out after lecture and make sure it's correct before I post it.
Cool, thank you.
But good catch, good catch. This is what I get for copying and pasting. Yeah. So yeah, so basically what happens is you end up with these two sets of sort of calibrated phases, which are decoupled, and you need to connect them to each other in order to get the crosshand polarizations, or the crosshand correlations correctly calibrated. And so in order to do this, you basically need, or well, to back up a step. So basically, if this is not calibrated, it has the net effect of shifting signal from one Stokes into another with these crosshand correlations. So with the linear feeds, it's Stokes U and V that are affected by those crosshand polarizations. And so if you don't calibrate this, Stokes U and V basically mix together. And this is what Ryan's been seeing in his data, am I right? Is because you're seeing some of these phase errors or XY phase calibration issues. You see Stokes U signal accidentally showing up in Stokes V. Is that a right description?
Yeah, exactly.
Yeah, okay. And so that's what happens with linear antennas. With circular antennas, it's Stokes Q and U. And so with circular antennas, without the phase reference, you actually don't know the polarization angle because Stokes Q and U are for the linear polarization, they define your polarization angle. And so with circular feeds, if you don't calibrate this, you don't actually have trustworthy polarization angles at all. And so in order to calibrate this, you basically just need a calibrator source for which you know the Stokes parameters. So you know what the true values of U and V are, or you know what the true values of Q and U are, and you solve for this phase difference such that it gives the correct Stokes parameters out, essentially. And it's a fairly straightforward thing to actually solve for. You just have to make sure you have the right calibrator source as part of your observation. And so sources without a suitable calibrator source like this can't actually be used for polarization analysis.
This is different than leakage into Stokes I, right?
Yes, yes. Okay. This is different. This is purely U to V and vice versa for linear and Q to U. So this is a very specific case, and it results out of sort of this physical origin. So leakage is actually, yeah, the next topic. And this is sort of a more general form where any of the Stokes can sort of leak into any of the other Stokes. And if you go all the way back to the Jones formalism, this shows up as off-diagonal elements. It's effectively signal from the X antenna leaking into the Y antenna and vice versa, and not being detected as the correct polarization. And then this when you transform it into Stokes parameters, it manifests as the Stokes parameters having values that are a little bit mixed together effectively. And the physical origin, well, let's back up a step. We break polarization leakage effectively into two terms. One is the direction independent version, which we call the on axis, and the other is the direction dependent, which is the next slide. And so for this on axis direction independent, the idea is to capture all of the coupling, the issues effectively that occur in the antennas and in the electronics. So something that doesn't depend at all on direction. So it's sort of the electronic parts of it. And the idea then is you want to try to remove this in calibration by having, so typically this means having a calibrator with known Stokes parameters, and you look at the differences between the known value and what you measure. And traditionally, it's quite often done using unpolarized sources, because the dominant problem with leakage is usually Stokes I into Stokes Q, U, and V. So you could have a unpolarized source that appears polarized, because I mean any source has Stokes I, but not all sources have Stokes Q, U, V non-zero. And so a lot of the traditional method was you find you take a known unpolarized source, measure it, see what its Stokes parameters are, and you say, okay, if Q, U, and V are non-zero, that's because of the leakage. Determine the correct calibration to set them to zero was sort of the traditional way. But in principle, you can do this with any source of known Stokes parameters. The off-axis leakage is effectively the direction-dependent effects. This is often associated with aspects of the dish. You can have imperfections in the dish that cause a polarization-dependent response. Things like support struts holding the secondary can have polarized behavior, stuff like that. All these kinds of effects like that. And in general, they are difficult to calibrate for, somewhere between difficult and impossible. Because typically, when a calibration is done, you point your telescope directly at the calibrator, so it's sitting right at the center of your beam. Then go through your on-axis calibration. And so you can calibrate everything such that at the very center, there's zero leakage. But in terms of the off-axis effects, you can't calibrate it on an actual observation directly, because there's effectively too many free parameters. As you have as a function of position, what is the leakage? And in principle, that can be arbitrarily complicated. So you can have an arbitrarily complicated function to describe it. And you don't necessarily have constraints, because you would have to have a source of known polarization at every location in the beam, which we don't have. And so the general solution to this is using holography data, which is something I'm not going to spend time on because I don't understand it that well. But what holography data basically does is it does directly measure the response of the telescope as a function of position in the beam. It kind of involves taking two telescopes, pointing them at the same source, and then sort of moving one of the telescopes around so that you're looking at different locations in the beam. And then seeing how the response changes as a function of moving through different parts of the beam. So you can basically map it out that way, hope it doesn't change over time, and then create a model and then apply that to your data, to all later data. That's one way, and that's sort of the most common. Some people have talked about doing, although I don't know if it's ever been implemented successfully, is trying to fit it to your data directly by sort of reducing the number of free parameters. You assume that the leakage has some sort of smooth function of position. Therefore, you don't need to measure every single point because you assume some kind of smoothness constraint that if you only measure it at a few points, it's not going to do crazy things in between. And so there are some ideas for how you can do that. We're talking about it in terms of ASCAP and POSSUM, but we haven't implemented anything yet. So, I won't say anything further. Finally, there is ionospheric Faraday rotation. So I haven't discussed Faraday rotation yet. That is the last topic. But effectively, this is a change in the polarization state that is introduced by the Earth's ionosphere. And that is not something that we like because it's a change from the astrophysical values. You know, we don't consider the Earth's ionosphere to be astrophysically interesting most of the time. And so we want to correct for it to get at the values as they were from space, effectively. And the ionosphere can change things in a way that depends on time and position. And so, for example, if you have a long observation and the ionosphere changes, if you go to integrate over time, it can mess things up if you don't calibrate for it. This was a big issue with LOFAR. And so this is predominantly a problem with low frequency observations. And for the most part, it can't actually be calibrated sort of just using your own data. It relies on having external measurements of what the ionosphere is doing. And so you have to have some these external measurements of the ionosphere and then model what the Faraday rotation should have been. And then you can try and correct that off in your data before imaging. And I wrote a whole chapter of my PhD on this, but I will spare you the gory details other than, yes, this is a thing that you have to do when you're sort of working with low frequency data. Any questions on the calibration part of it before I go on? All right. So I wanted to say a few things about sort of the practicalities of doing polarization measurements with radio data. So as I was saying a little bit earlier, Stokes parameters can be computed in visibility space because they're just linear combinations of correlations. And then once you've defined it there, you can go through the entire imaging procedure as discussed in the previous lectures. In theory, you could actually go through the whole imaging process directly on something like the XX correlation or the YY correlation. It's just not physically meaningful. So doing it in terms of the Stokes parameters is the default. And so everything that I already discussed was basically doing this for Stokes I. And so the only sort of additional complexity in terms of like the imaging and such is we now have 3 additional Stokes parameters which give the full polarization information of the signal. So the Stokes QUV. And so most imagers have built-in options to let you do this. You can either image all 4 Stokes or some subset of that. And doing so gives you the full information on the polarization content of the signal as a function of, you know, position on the sky, and sometimes importantly, the polarization as a function of frequency, which of course is very critical when we get to Faraday rotation. And so all of the Stokes parameters are basically subject to all of the properties of imaging as discussed. They all have a point spread function. Typically, it's the same for all the Stokes parameters in a given data set. They all have to go through imaging and clean. They'll all have image artifacts, which may not be the same because they can have some slight differences in the processing that gives them different artifacts. They all have their own noise levels, although they're usually linked. All this stuff is sort of present in all the Stokes, and there tends to be relationships between all these aspects. There's a number of different kinds of quantities that tend to come up a lot. So the Stokes parameters themselves are basically our direct measurements in terms of what we get off of polarized imaging software is you get the Stokes parameters as images, and then there are sort of different operations you can do to get at physically interesting information. For example, linear polarized intensity is the combination of Stokes Q and U in quadrature. This defines the intensity of the linearly polarized component of the wave. You can define a total polarized intensity by also folding in the Stokes V component as well into that. And so this tells you how much of the intensity is polarized, and you can then compare that to the total intensity to work out a polarized fraction as either the linear or the total polarized intensity divided by the total intensity of the wave. And so this is effectively telling you how strongly or how uniformly polarized a signal is. A signal with 0 net polarization will come out with a polarized fraction of 0. And in principle, all Stokes parameters Q, U, V should be 0. Sometimes we'll also define fractional Stokes parameters as Stokes parameter divided by the total intensity. This has some useful applications in some forms of Faraday rotation analysis. I won't have time to get into, but for the sake of making sure that you see these definitions. And circular polarized fraction is sort of logically defined with noting that Stokes V is a signed quantity. All the Stokes Q, U, and V are all signed quantities. And so in order to define the polarized fraction in circular, you just take the absolute value so that you're not distracted by it being positive or negative in terms of the fraction. So one thing that I have kind of not brought up until now is the issue of coordinate systems in polarization. So your antennas, if you have like an X and Y dipole, they're fixed to your instrument, to your telescope, which they may not match up with the orientation of the sky. And you can have parallactic angle effects, which I discussed previously, where the sky is rotating and that changes the relative angle of your object relative to your telescope sitting at the ground. And so while the measurements are in the instrument sort of frame of reference, whatever that might be, whenever we want to talk about Stokes parameters and polarization in an astrophysical sense, we want to do it in the sky frame of reference, and in a universal frame of reference that is reproducible between observations. And so there is a uniform standard defined by the IAU for this, which is that 0 polarization angle is always northwards towards the north celestial pole, so towards declination plus 90. And polarization angles increase to the east from north. Yeah, I'm not sure how the mirroring is going to do this, but increase to the east, so that pointing sort of eastwards or towards positive right ascension is a 90-degree polarization angle. And we also define, so because we've defined 0 to be northwards, positive Stokes Q is northwards polarization, and negative Stokes Q is eastwards, and so on for Stokes U. Although I do kind of want to note that sometimes in cosmology, they have a different convention for angles. I don't know why, and it is a little annoying. And I'm pretty sure the IAU is on our side, so I'm not sure why they do it.
Yeah, I know Planck does that, even like not even just in like a cosmological context, but there's like Planck in general.
Yep, because Planck is a cosmology mission.
Yeah.
And so all of their data products are defined for the convenience of the cosmologists.
Yeah, that's what forced me to learn this.
And so conveniently, it is not that big a fix, because all it actually does is it changes Stokes U to minus U, as we would define it. So it is a convenient fix, but it is annoying as hell if you don't know about it. So now you know. And so it's something to keep an eye on if you're getting data from cosmology projects, I guess. I think the reason it's defined differently is because it affects the handedness of certain quantities. and it's more convenient for them to have certain-handedness in the way that they do it, I guess. This is my vague understanding, but yeah, be aware of that. And yeah, I'm not going to have time to go through everything I want to discuss on Faraday rotation, but since I'll just sort of go through it very, very quickly, because this is, you know, a topic I am very fond of. So we know that magnetized plasma, such as exists in the interstellar medium, is birefringent, which means that different polarization states have different indices of refraction. And since the index of refraction defines the phase velocity, this means that different polarization has different phase velocity. And in the case of plasma, it's specifically the circular polarizations that are different. So left circular and right circular polarizations have different phase velocities. And so as they propagate through a medium, you can sort of think of, you know, a linearly polarized wave goes into a plasma, but it's actually a superposition of the left and the right circular. But one of them propagates a little bit faster than the other. And so the phase relationship between them changes. And the phase relationship between circular components relates to polarization angle. There's a whole mathematical derivation on that I skipped, but that's how it goes out. So the net effect is a linearly polarized wave goes in, goes through the magnetized plasma, it comes out with a different polarization angle. And the change in the polarization angle is proportional to the wavelength squared and a path integral of the magnetized plasma, the electron density of the magnetized plasma, and the magnetic field component along the path of propagation. And so for sort of convenience, we basically define this constant, you know, this integral factor as something called the rotation measure or the Faraday depth. And there is a distinction between those terms that I don't think I'll have time to get into today. But rotation measure or Faraday depth, and then the whole change in the angle is that times the wavelength squared. And so this is interesting because this gives us a mechanism to study magnetized plasma in the interstellar medium. Is if we have some background polarized source, we observe it, its emission has passed through the plasma, therefore it's experienced Faraday rotation and we can learn something. The traditional method is you observe over some range of frequencies or equivalently some range of wavelength squared. And just because of this equation, which comes out of the physics of Faraday rotation, the polarization angle changes linearly with wavelength squared. So we simply measure that slope of the measurements, and that is the rotation measure. And then that then gives us some information on the magnetized plasma that we can then go on to try to model and understand. This becomes slightly messier in the sense that what if we have multiple sources of polarized emission along a line of sight? So every source has some polarization as represented by some vector on the Poincare sphere. And if we're detecting multiple sources of emission, the net thing that we're measuring is the superposition of all those vectors, the sum of all the vectors. And as I mentioned earlier, adding vectors in spherical coordinates is messy, and so the net result is that polarization angles do not add straightforwardly. And so if you have two sources of radiation, on top of each other, the measurement of the combination becomes much more complicated, and you've lost your nice linear polarization angle behavior. And this gets even worse if you stop to think about how synchrotron radiation is produced anywhere that you have cosmic rays and magnetic fields. Faraday rotation occurs anywhere you have thermal electrons and magnetic field, and so they can be co-located. And so you then end up with some combination of emission, with different amounts of Faraday rotation, and it's all superimposed and the vectors are adding together, and the output result is just messy. And so how do we then go about trying to analyze a complicated signal, complicated polarization signal like this to extract Faraday rotation information? And there are a couple of different algorithms that can be used to try to extract this kind of information. One of the most common ones these days is rotation measure synthesis. And in view of the time, I'm not going to go through the full discussion about this, but the short answer is we can basically exploit a sort of the mathematical structure of how Faraday rotation looks, and we can take the polarization that we measure as a function of frequency or as a function of wavelength squared. And it turns out that the mathematical form is right, that we can define a Fourier relationship between this and the polarization as a function of different possible Faraday depths or different rotation measures. And so how you establish this mapping is a slightly complicated issue. I would invite you to look at Vanek 2018. I wrote a paper on this. And I think I was somewhere between the second and the fourth person in the world to actually sit down and write out how you end up defining some of these quantities. It's a bit of a mess, but the end result is you can establish this Fourier relationship where you measure polarization as a function of wavelength, you Fourier transform it, and in principle, you can get the polarization as a function of how much Faraday rotation it has. And there are issues with this, like the fact that you don't measure every possible wavelength, every possible frequency. So you, like with interferometry, there is missing information. You have a point spread function. You have to kind of deal with sort of equivalence of the short spacing problem and the resolving out of emission and finite resolution and all of these kind of related issues. But in principle, this gives you information then on the polarized emission and how it behaves in terms of how it's distributed over different degrees of Faraday rotation. And that's all I really have time to talk about, although I am happy to discuss this offline, as people in Brian's group already know. And so this method can be somewhat generalized in the sense that you can do it not just for single lines of sight, but for the entire sky, which is a technique we call Faraday tomography, where we can map out Faraday rotation across huge chunks of sky to learn quite a bit more about the Faraday rotation behavior over large chunks of our own galaxy. And yeah, that is where I think I'm going to end things. So thank you for staying through the entirety of this course. Here I am rewarding you with a picture of 20-year-old me at the VLA. But otherwise, that is basically all I have to say. So are there any questions, I guess, before I wrap up?
No, thanks, Cameron. Yeah. Also, I'm jealous that you got to go to the VLA.
Yeah, this was a bribe. This was a bribe from my undergrad supervisor, who said, "I will send you to the VLA, but then you have to do a good job reducing the data." It worked.
It was worth it.
There you go.
But anyways, yeah. So this is the end. Other than the homework, I guess, for the people doing that. But yeah, feel free to send me comments, feedback, questions, questions about any radio astronomy stuff, about polarization, about whatever. I'm not going anywhere in the short term or in the medium term, so I'm happy to just keep discussing this beyond the scope of the course.
Awesome. Thank you so much. That was really good.
I have a
lot.
Mm-hmm. Yes, thanks, Cameron. That was really helpful. I have a crazy question.
Yeah.
I've thought about this for the past couple of months, and maybe I mentioned it to you in the past. But okay, so like we know that one of the definitions, I guess, of Faraday rotation is, like you mentioned, the fact that the circular polarizations have different phase velocities.
Mm-hmm.
And I'm wondering, and relating that to like the dispersion measure, where it's also operating kind of in a similar way in the sense that there's different phase velocities as a function of frequency.
Yeah. It's the same process, actually. It's the same process, and like the plasma physics derivation is basically the same. The only thing that changes is when you add a magnetic field, there's a bit of a symmetry breaking. So with no magnetic field, left and right circular have the same plasma effects. So it's the same.
Yeah, exactly.
Yeah.
So I'm wondering is there possibly a way to like, so normally the way to observe a DM from a source is the condition has to be that it's a transient sort of signal and a coherent emission mechanism that's causing it. I'm wondering, is there a way to like use the fact that if a source is polarized but persistent, can you get the dispersion measure by using the fact that it's polarized? Like if there's some degree of variability intrinsic to the source, then is there a way to pull out the DM out of that? But see, like this is where I think I'm confusing like a coherent emission mechanism to a polarized, polarized emission, which is not necessarily like coherent.
No, I mean, is it actually a requirement that it be coherent in order to get a dispersion measure? I don't think that's actually a requirement.
That's what I've read, but I haven't come across. I don't think there's a lot of research on that from what I've seen, but yeah, it was just something that I've thought about in the past because it would be interesting. But.
Yeah, it's not obvious to me off the top of my head, but if there is a method to do it, it would be interesting but subtle, I think.
Yeah,
it would require looking into the mathematics of it a little bit more carefully than I can do off the top of my head.
Yeah, I find it's very confusing going back from circular to linear to understand Faraday rotation, because it's like you can describe a linear polarization as in terms of a circular basis,
right?
But you can still have a source that's 100% polarized, but described in a circular polarization basis, which is bizarre.
The circular basis is really counterintuitive.
Yeah,
and I have made peace with it by virtue of the mathematics. I've gone through a couple of plasma physics textbooks and like looked at the derivation of Faraday rotation, and it's scary as hell. But if you suffer through it, it kind of helps a bit.
Yeah.
Yeah. All righty. Last call for questions, comments.
What's the most exciting thing that you would like to be seen done with when it comes to polarization?
Oof. That's a big question.
That's a loaded question.
Yeah. For me, the future of Faraday rotation work is ultra broadband.
Yes.
Ultra broadband. And so there's almost no data sets that exist like that yet. So like Craig Anderson, I think, did some work, or maybe it was Shane O'Sullivan, did some work that went from like 1 to 10 gigahertz. And it was amazing. But it was difficult to get that data, and it was a very limited data set. So doing that with a lot of, like a big data set with a lot of objects with maybe even diffuse emission is super hard. And
difficult for instrumental reasons.
Partially, I mean, finding receivers that have like covering like the full frequency range is basically impossible. And so they did it using ATCA, because ATCA had receivers that covered the majority of the frequency range. They still had to do it as like 6 separate observations, just because like that's the amount of instantaneous bandwidth that they could accommodate. But you know, getting that kind of data just takes a lot of observing time, and we can see that now, like with Possum, for example, right? ASCAP goes from 700 to 1800 megahertz in theory, but it can only observe that in 288 megahertz chunks. And so the question is do we cover the full range in 3 or 4 chunks? And no, we're not going to get the observing time. And so we're going to be stuck with 1, maybe 2 bands out of that, just because of the observing limits. And so I'm a little cautiously concerned because, for example, SKA is going to have massive bandwidth, supposedly. That's part of what they're building it for. Is it's going to be a very broadband instrument. But how much of that are we going to get in one shot? Because if you have to do it in 6 different observations, how on earth are you going to get enough SKA time to get 6 different frequency bands for however much of the sky you want to cover? It's going to be hard, especially when you combine SKA low and SKA high. So I don't know. That's what I think the future is, and I don't know how we're going to get there.
And I guess in general, having like a broad bandwidth is beneficial, well, for many reasons. But one of them is it gives you better, more accurate RM measurement, but then it also gives you information about how the polarization properties change as a function of frequency.
I mean, and there is some value for Stokes iWorks, like spectral index. You need to observe it at as broad a range of frequencies as you can. And so there's value there, but it's not always enough value to convince other people to do it.
Yeah.
So yeah, we'll see what's happening. I mean, GMIMS, for example, is a heroic effort to go from 300 to 1800 megahertz. So that's like a factor of 6, and it's with single dish data. And that is like a 12-year project to get that done. Just covering the entire sky across that frequency range. And it's going to be a very good data set, but it's also suffering a lot of challenges of its own.
Yeah, I'm waiting for the data set to come out because they have a north and south, right?
Yeah.
I think they've released the south, at least for like a limited frequency range. I think they've released.
Yeah, well, yeah, they lost a lot of their frequency range to RFI, so that's another problem. But yeah, so because you've got me going, and I'm not going to stop. So doing ultra broadband stuff has some really big problems. I mean, RFI is a big one because you can't control that. You're going to lose huge chunks of bandwidth to man-made, observing bands. So like, the FM band is shot. Huge swaths of the satellite band are just shot. Like you just can't observe there at all in some places. So there's so much you lose there. But also, as I said, getting receivers across the huge range of frequencies is hard. But then things like resolution matching and interferometer filtering. I mean, if you think about 1 gigahertz and 10 gigahertz, factor of 10 difference in frequency, if you do it with an interferometer with the same baselines, that's a difference in a factor of 10 in resolution, in what your shortest baseline is and what you're filtering out. in terms of like even just that all of your baselines in terms of how long they are in terms of units of wavelength scales by a factor of 10. And how does that affect your ability to look at resolved sources? It's a nightmare.
And I suppose it'll even change the properties of the diffuse emission as well, I guess, because if the beam if the beam width is changing, then also like instrumental effects like beam width depolarization will change it.
Yep. Yeah. I mean, some of that you can correct in post to a degree, but
yeah, because you know how it behaves, I guess, right? So you can look for it. And,
yeah. Well, with stuff like resolution is you can always make it worse. So you can take, a factor of 10 in frequency, and even if the high end has 10 times better resolution, you can degrade it by a factor of 10 to have the same resolution. And the problem is yeah, your resolution is as bad as your worst resolution. And you've lost information there. And in the case of stuff like resolving out structure, some of that you can't fix. I mean, you can have like an extended, like consider a supernova remnant, for example. Maybe there are features there that you would detect at the low frequencies because your baselines are the right length. And then in the high frequency data, it's just gone. And so if you try and do RM synthesis where a thing is there in part of the band and it's gone in the rest of the band, it's a nightmare. So I'm being very pessimistic right now, but I mean, this is why no one has done it yet. The scientific value is enormous, which is why someone will do it someday.
Yeah, it's interesting.
Yeah, maybe me. I don't know yet. Brian is pestering me to start new science projects. Maybe this is one of them. But anyways, we have reached the end. At the very least, I have 9 chat messages that I've not read, so hopefully those weren't important. But I am going to stop the recording here at the very least.